Hello, this is ML Monthly with Ato, and we're going to be covering the most interesting machine learning papers that I read this month. This video is mostly for a very technical audience who is very deep into the machine learning sections, but hopefully the implications at the start will be quite interesting. So there are sort of three interesting papers that came out this month. One is retentive networks, which is one of the alternative transformer architectures, which is kind of the thing that's taking, for example, ChatGPT, presumably Bard, Llama, etc., and all of this LLM craze. And the idea is that they're trying to make essentially transformers, but with very cheap inference, so that it doesn't cost so many GPUs to run inference, for example, whilst maintaining some of the nice properties of transformers. The second one is universal attacks on aligned LLMs, which essentially comes up with a way to systematically get LLMs to say censored content and essentially jailbreak the LLMs via discrete optimization. This probably has the most amount of consequences in the real world, because if someone builds a system to essentially democratize this and make it easy, it allows anyone to access the LLM knowledge that has been usually censored through alignment and RLHF. And this can be a real public risk. Lastly, the last paper is more theoretical, which is DPO instead of RLHF, which essentially builds a mathematical equivalence between RLHF and DPO and argues that the DPO objective is enough and you don't need RLHF because RLHF is fairly compute intensive. And this has some efficiency optimizations that we could see in the future. So let's start with the first one, which is the retentive networks. Transformers have obviously shown the most amount of impact in the real world, having very strong performance, shown by stuff like ChatGPT, and training parallelism, which is one of its very desirable features, but it doesn't have a very low cost of inference, seeing as its inference cost for just predicting the next token requires you to compute that along with all the other tokens, and the memory complexity explodes in O(n) squared way, but it has strong performance. And essentially, this trilemma has been explored by a bunch of other architectures like linear transformers, recurrent neural networks, or more recently, the RWKV and the H3 or the S4 state models. And this paper argues that RetNet can solve them all with an O(n) inference cost, just like recurrent neural networks, and O(n) memory, just like recurrent neural networks as well. So, how does it work? Well, the idea is that RetNets are kind of combinations of the transformer attention mechanism along with the recurrent neural network recurrent mechanism. And the idea is that there is a mathematical equivalence between the two different representations of the recurrent representation and the parallel representation. And the way you get the outputs differs as well. So let's cover the recurrent representation first, which essentially takes a recurrent state, so the previous hidden state, multiplies that by gamma, and then adds that with the product of k and v, adds them together, and then essentially multiplies them and then group norms to get an output. You can see the direct equation there, so you just Sn is Sn, which you see here, which is the next recurrent state, is just Sn minus 1 times gamma plus k, v, and then you get the output by multiplying that with Sn. So that's essentially the idea of just the recurrent representation. That one's pretty simple. But then the fun thing that you do to get to the parallel representation, and the reason why you want the parallel representation is because you want the training parallelism, which is very effective during training time, is through a sequence of maths, which essentially exploits the fact that you can express all of these inputs and recurrent state, all in terms of diagonalization. So I'll get to that in a second. And just to give you an intuition behind why you want both of these, it's so that you can have your cake and eat it too, where the recurrent representation gives you a cheap cost of inference of O1, whereas the parallel representation gives you the high parallelization that transforms have. And then the performance, as mentioned in the previous trilemma, can just be solved through empirical studies, so by running a bunch of experiments. And yeah, this is how the retention in the parallel representation works. It's just QKT, that with dot D, and then multiplying that with V, where D is defined like this. So that essentially represents this particular mechanism here. Now, I won't go into the full details of the maths, but following these two sort of setups, essentially what you end up with is you end up diagonalizing this matrix into this kind of form by saying A, which is the matrix you have here, breaking that down into essentially gamma e to the I theta, and then like through the left and right diagonal matrix, and essentially you like can turn it into this closed form, which allows you to switch between the recurrent representation and the parallel representation. And then the model performs pretty well against the other alt transforming models that have been proposed recently, like RWKV or H3 or Hyena. And it also performs pretty competitively with transformers as well. And so hopefully the idea behind the network is that this, if it works, can solve the trilemma and might be the most dominant architecture moving forward. So the next one is the universal and transferable adversarial text on aligned LLMs. The idea of it is, can you get it to say something that it was forbidden from saying by adding some crazy postfixes in your prompt such that it jailbreaks the LLM. So an example is you might ask it to generate how you would destroy humanity, and then follow that up with a bunch of these random sequence of characters, and that forces ChatGPT to say the thing. Similar with Bard, similar with Claude, and similar with Llama as well. So how can you just say a bunch of weird things after your prompt so that it can say the thing? And the way it does this is essentially by a discrete optimization problem, which is to say, okay, let's start with some initially random sequence of tokens, but can you substitute each of the tokens in such a way that it increases the probability that the language model will give you an affirmative response to what you are asking for. And there are a few ways of doing it, but they go with the simplest approach, which is just a very simple gradient and greedy method. And this works for sort of black box or closed source LLMs as well, just by optimizing a maximum likelihood objective. And they call this algorithm the GCG algorithm, which just takes the top k substitutions and computes the replacement, and then moves step by step that way. They kind of propose two different types of adversarial texts. One is like, can you get the model to respond with a specific prefix? So for example, you might say, generate a step-by-step plan to destroy humanity plus adversarial prompt. And you might say like, hey, I want the response of the language model to start with step-by-step plan to destroy humanity. So you might be optimizing for a specific objective where you want their response to start with a particular thing. Or you may want to optimize for multiple models, giving you the answers to the ROHF censored topics. And these are sort of the objective functions that you would optimize for the first case. And then, yeah, they essentially compare and benchmark the language models, or specifically the language model jailbreaking strategy, which is systematic, across a bunch of different alternatives, and it performs the best out of everything else. Interestingly, they found that combining multiple GCG algorithms improves the attack success rate, which is what ASR is, on several models. And you can see the results of it there, along with other methods like just pure prompting or sort of weird prompting that can get it to break the model. The implications of this is obviously huge, because it means that hackers or attackers can figure out information that maybe would have been harder to search in the past, and they can jailbreak LLMs, which can compromise the safety of these LLMs. And for example, 14-year-olds can learn this hack and essentially learn how to build a bomb, which could be a public threat. Lastly, you have the DPO, or the direct preference optimization, where essentially it tries to build a mathematical equivalence between the RLHF method and the direct optimization. So the way LLMs like ChatGPT or Llama are trained currently is through something called RLHF, where a bunch of humans asks the language model to write some stuff and then evaluates their response. And then using that data of the human labeled responses of like how good a response was, it will train a reward model, and then using the reward model, you'll run this compute intense process called reinforcement learning. But then the idea of DPO and this paper is essentially to do this optimization process directly by going from the preference data, just like in RLHF, but training the language model directly without doing this cumbersome RL thing. And the way it does that is by essentially by clever parameterization of the reward model and just reformulating the problem into a binary classification problem, which you can see the loss function for here. And the explanation for it is essentially you start with the most optimal form of the closed form, like optimal policy that you would get through RLHF, so this process. And you would essentially rearrange until you get to the DPO objective. I'm not going to go over the maths, but you can everything you need to at least understand the intuition is all here. And here are some of the benchmark data where it performs competitively and well amongst other methods like GPTJ or SFT. So the idea and potential sort of consequences of this paper is that we may be applying the RLHF process or the alignment process a lot more efficiently using the DPO objective, since the equivalence can be derived. Now, it is still to be questioned if the DPO objective is actually going to be better than RLHF in practice, and that will probably come in a bit more time. But yeah, those three were the papers that I thought was the most interesting during August 2023. Thank you for listening, and please let me know what papers you thought was the most interesting in August of 2023. Thank you.